will look at a very different problem. In this case, you were the nice guy. You wanted to provide water from source to the sink, correct? But nice guys are not fun, right? Fun happens when you try to destroy things or, okay, I'm joking, but okay, here our life will become interesting if we say, how can I make sure that no water reaches from source to the city, okay? So once again, assume you are a terrorist or, whatever, terrorist for one, or spy for another country or whatever, and you want to make sure that from correct, and obviously all bad guys are lazy. So if you want to stop getting everything from here to here, one simple strategy is cut all the pipes, right? But that's not great. That is expensive, or we are lazy, or we don't have resources to cut all the pipes, right? So in that case, you want to cut minimum pipes such that no water reaches. Yes, no water reaches from, as they were saying, I want to cut minimum number of pipes such that I want to sum up the capacities of those pipes. Why am I summing up the capacities? Because intuitively I can assume CUV is the amount of effort to cut pipe U, V. Right? If the capacity is big, pipe is going to be bigger. I need more resources. Agreed? This is called the Min-cut problem. I probably should not have erased the image, but something like this, right? And then what does it mean? How do I make sure that what does it mean that if I cut some pipes, no water reaches from S to T? What does it mean mathematically? Can I describe it as a nice condition? There is path or there is no path, right? So if from S to T I can cut it, it means there is no path from S to T. Can I make it more precise? Can I simplify it? Because this paths, there are so many paths, right? Anytime I cut the pipes, I will have vertices which are still connected to S and vertices which are not connected to S, right? So cut means I cut some edges. Every cut specifies S and S bar, where S is the set of vertices connected with S. Agreed? Right? Set of vertices connected with S, and correct. And if I want to make sure that S and T, I have no water going from S and T, that means what do I need? Right. So and what should be part of what and what should not be part of what? Right. So this is the definition of a valid cut. Okay. So I can take any subset of my vertices which contain small s but not t. Then whatever edges are going from S to S prime is the capacity of the cut. Okay. So now we have another problem. We have for given a vertex at S and T, we can define valid cuts. Cuts are specified by a subset of vertex which contains S but does not contain T. Right? And given this cut S, I don't even have to specify S bar. Given this cut S, this is the capacity of the cut. And then the problem of the terrorist is to minimize the cut. Agreed? And now, if you believe in the beauty of mathematics and probably linear programming, you have a problem here, you have a problem here. What do you anticipate? You anticipate that this is the this. Okay, let's try. So why don't you write this as a linear program? Don't take the dual of this. As a mathematical problem, let's write down the let's write down a program for this, an optimization program for this. Hopefully a linear program. If it has to be dual, then it has to be a linear program, right? So, and if you realize we did something like this before, right? In the exam we had matching and covering, and we made a program and then converted it into a linear program. So what do you think? What would be you start with a program for this. What should be the variables? What should be the equations? So if you cannot come up with a program, where are you stuck? Right, so that is how we will define their values. Remember, like maximum matching, what did we say? We said whatever is part of matching, we will call it 1. Correct? And whatever edge is not part of the matching, we will call it 0. Right? So let's start with that. Let's say Pu is the variable. I'm just not writing it as XU, so that forum has to change everything and change all the variables. So Pu is indicator of whether U is element of S or not. Correct? Makes sense? This is the simplest thing which will be so helpful for you all the time, this indicator variables, right? What it means is, just to clarify, this takes two values, 1 and 0. It indicates when it is 1. It is 1 if U is element of S, 0 otherwise. Okay? This is called an indicator variable. You can replace this by any proposition or any formula, right? So anything which can take a true or false value. So whenever this is true, variable takes value 1, otherwise 0. Like in matching, X was part of the matching. Correct? What happened in the word cover? otherwise 0, right? So this is suppose PU. Is this sufficient? What is the thing which I want to optimize? Summation PU CUV. Good. Is this the correct? This capacity will only be counted when PU is 1 and PV is 0. Sorry? Minus into, okay. This is a problem, right? Why is this a problem? Not linear, right? You are multiplying PU by PV. What about this? Yeah, sometimes it will be 0. Oh, are you seeing this? Obviously, the issue is reverse edges will start counting here. We only want one side edges, right? So it will subtract the capacities of edges going from S bar to S, right? Which we don't want. We wanted to show dual, we can't even write a program for it. And I will give you the solution because I know forum has a solution. The idea is exactly. This is indicator UV is part of the cut. Okay, and remember how we defined the cut? Edges going from S to S bar. If we do that, then first thing becomes easy. Correct? This is not. But now, what are we stuck with? Validity, right? It should happen that if PU is 1 and PV is 0, similarly, if PU is 0, PV is 0, then DUV should be 0. So how do I enforce that constraint? DUV plus once again, anyone who does not have a pen and paper, so here, okay, the first try could be this. Okay, this almost works correctly except, right? So this almost works correctly except when U is element of S bar and V is element of S. Then you will have infeasibility problem, right? Like you will have some UVs where this is 0, this is 1. And if you are saying enforce the condition DUV greater than equal to 0, that we will do. But if we just do this, then we will have no feasible solution. Because for any sensible cut, or we will only have trivial solutions, any sensible cut will have somewhere this will become 0, this will become 1, I cannot find a DUV for this. And this is where linear programming actually saves us. Why? Because what are we trying to do? We are trying to minimize DUV, right? So if PU minus PV is 1, minus 1, to be 1. When this is 0, since we are minimizing, this will automatically make it 0. For the other direction, when this was minus 1, this constraint will again force it to be 0 because we will have this constraint. Take some time to think about it, but there is a nice little trick which can be used basically because we are working in this optimization domain. We are trying to optimize in any sensible or any good solution of this. We are anyway trying to optimize. We are looking at the optimal solutions. There might be some frivolous solutions, but the useful solutions will make sure whenever this is 1, this will be 1. Whenever this is 0, this will be 0. Whenever this is less than 0, this will remain 0. Make sense? Because we want to minimize this. By the way, we also want, so I will just write this constraint explicitly, right? We are, yeah, but that won't, that will be counted here. That won't be. Yes. Sorry, I don't want to erase this, right? Yeah. So, are you okay with this change? The only thing here now is where I am constraining PU, PV, DUV to be. Correct? At this point, if I want to exactly correspond with the cut, I want PU as well as DUV to be element of 0, 1. Notice the curly brackets here. There is an indicator variable, so I say that I constrain them to be between 0 and 1. Sorry, not between 0 and 1. They should be exactly 0 or 1. So, what you want to convince yourself is that the optimal solution here will be the min cut solution. There is a small change here, but then if you look at any solution here, correct, what will happen? Only DUVs which are 1 will be the case when PU is 1 and PV is 0, right? So, then I define my cut to be wherever PU is 1, and then that will be a valid cut because I will keep DUV to be 1 only and only if this is in S, this is not in S. So, this is what you want to be sure of. That is saying if and only if PU is equal to 1 and PV 0. Okay? Sounds good? So, we are very happy. We have a linear program for max flow problem. We have a integer linear program for the min cut problem. So, clearly they cannot be dual of each other. Okay. So, before I talk about the relation between these problems, I want to talk about ILPs. or integer linear programs. These are almost linear programs where some variables are constrained to be integers. Okay? And clearly ILP subsumes LP, right? Because I'm allowed to put one more constraint. I can put linear constraint on my variables, as well as I can say that my variable should be integers, right? So now you remember we in the beginning about nice. Linear programming was nice because it captures lot of problems and it has efficient solution. It has good algorithms to solve it, right? Simplex was one. It was not efficient, but was a nice algorithm, and we know nice algorithms exist. So now another question could be, what about ILPs? For LPs we have nice algorithms. Do ILPs also have nice algorithms? What do you think? Why? No, you have to expand your solution approximately. No. You are saying how ILPs are useful, but do you believe ILPs are efficiently solvable? Yes or no? So what is the argument for no? Okay, good. So intuitively, our feasible set was convex, like nice continuous one, right? Now, once you force it to be integers, the niceness of our feasible set has been lost, right? You can say it in multiple ways, but more importantly, this is just an evidence in some sense. But actually, we have a much concrete evidence that this is very, very hard, because many NP hard problems can be written as integer linear programs. Okay, and if you are familiar with some, you can take the max independent set problem and write it as an integer linear program. Okay, and we obviously, not obviously, but most of us believe that NP hard problems cannot be solved in polynomial time. Right? Coming up with a solution is much harder than verifying a solution. And if that is the case, that means ILPs in general cannot be solved in polynomial time. Okay? So other way to say it is, NP not equal to P implies ILPs can't be solved efficiently. Right? One thing which I want to emphasize here is that when I make such a statement, I am saying this about the generic class. There could be specific LPs, specific ILPs which I can still solve. This is going to be an example of that. Okay? So just because something is ILP does not imply that it is hard. What we know, just because it is an ILP does not mean it is easy. It might be easy, it might be difficult. Do I make myself clear on this? Right? Okay, good. So with this knowledge now, we are stuck here. We have D prime, which is an ILP. Right? And we don't know whether it is easy to solve or hard to solve. But we have a trick up our sleeve. Remember the trick which we did in the exam also? What is the trick? Yes, we make it a linear program and ask, does it change the value? Okay, so the trick is, let's make it a linear program. Let's change it to the interval 0, 1. First good thing about this is that this is a linear program, right? That is a great news. The bad thing about this is the solution here could actually be, it could be non-integer, but what is its relation with the min-cut problem? The solution of this, smaller, right? Because this is going to have many more solutions as compared to the ILP, right? So this is going to be smaller than the min-cut, the actual min-cut. Question is, can we show that they are close? And this is where your suggestion of, sometimes we can take these solutions, make them integer and not lose much. This thing is called rounding. We will study about it. What I am trying to say is, this is a generic technique. This is a special case. Here, things are going to be wonderful. That doesn't happen generally. We have an integer linear program. We convert it into a linear program. We generally want to say that they approximate each other well. Even that is not true in general. Mostly, the way we show that they approximate each other well is, you take the solution of, let's say, this d. This has some fractions involved. You want to convert them into integers and still keep the feasibility. This is called rounding. It looks like rounding, right? We say, oh, if it is 0.3, let's make it 0. If it is 0.9, let's make it 1. After that, we have to say that our solution is feasible and we haven't lost much in the objective value. We will see many examples of such rounding techniques. Okay? So, this is a standard technique where we convert an ILP into LP by making the variables continuous. Sometimes we don't lose anything. Sometimes we lose a bit. Sometimes we don't get any guarantees. But any time you are stuck with an integer linear program, it's worth converting into an LP and asking, is this LP a good enough approximation of my original ILP?